Hello everyone. In this lecture we will discuss application of Gauss law. So here, according to Gauss law, E dot dA is equals to 1 over epsilon r times the total charge enclosed within that surface. So to apply this Gauss law on different problems, first we have one basic assumptions. First is E and dA are in the same direction, and second assumption is we require symmetry. We have three types of symmetry. First is the spherical symmetry, that is, make your Gaussian surface a concentric sphere. That is, suppose the radius of the circle is r, then here we have a Gaussian surface. This is a Gaussian surface. And the radius of this is small r. Okay, so here the Gaussian surface and the actual sphere, basically they are concentric. Then in second symmetry is the cylindrical symmetry. Here make your Gaussian surface a coaxial cylinder, that is, make your Gaussian surface a coaxial cylinder. That is, here this is a Gaussian surface. Similarly, we have third symmetry, that is plane symmetry. So here suppose this is a plane, and here in this case we will introduce one Gaussian pillbox. This is known as a Gaussian pillbox. This is the above the plane, and here this dotted line shows below the plane. So area of this pillbox is A, and this is known as a Gaussian pillbox. So here we have three symmetries. One is spherical symmetry, second is the cylindrical symmetry, and third is the plane symmetry. Now we will discuss problems related to these symmetries. So this is a first problem related to spherical symmetry, that is, find the field outside a uniformly charged solid sphere of radius r and total charge q. Now here, according to the problem, suppose here we have a sphere of radius r, and here for symmetry point of view, here we have a Gaussian surface. This is a Gaussian surface, and the radius, suppose this is small r. Now according to Gauss law, E dot dA is equals to 1 over epsilon naught time the total charge enclosed. So as we discussed in one of our assumption, E and dA are in the same direction. So here the left hand side, that is E dot dA, this is equals to E, and here we have a dA. So the area of the sphere is equals to 4 pi r square, and total charge enclosed within the sphere, this is equals to q, so as given in our problem. So now substitute these values in equation first, then we can write E 4 pi r square, this is equals to 1 over epsilon naught times q. Okay, or we can write E vector, this is equals to 1 over 4 pi epsilon naught into q over r square, because this is a vector quantity, so we can write r cap here also. So electric field here, this is equals to 1 over 4 pi epsilon naught into q over r square into r cap. So this field, the electric field here, so the field outside the sphere is exactly the same as it would have been if all the charges had been concentrated at the center. Okay, so this is the problem related with the spherical symmetry. Now we have a next problem related with the cylindrical symmetry. So related to cylindrical symmetry, we have a problem that is a long cylinder carries a charge density that is proportional to the distance from the axis, that is rho is equals to kx for some constant k. So here find the electric field inside the cylinder. So as per this problem, here we have a one cylinder and here this is a S, that is the radius of the cylinder, and length of the cylinder is L. Now here we require the Gaussian surface. So this is a Gaussian surface. That is a cylindrical symmetry. So by symmetry we have direction of this is a direction of electric field in upward, or this is a the downward. Okay, again this is a Gaussian surface. Okay, so according to Gauss law, E dot dA is equals to 1 over epsilon naught times the total charge enclosed. So here E dot dA, we can write E dot, here we have a dA, or then the surface area of the cylinder, this is equals to 2 pi SL, and Q, that is charged, total charge enclosed, this is equals to, this is the rho dV, that is rho is the volume charge distribution, or this rho, as we discussed as given in the question, the rho is equals to Ks. So now when we, so here we have rho is equals to Ks. So here we will use the cylindrical coordinates. So according to cylindrical coordinates, we have S ds d phi and dz, or we can write ks2 ds or d phi or dz. So this limit is vary from 0 to s. For angle it varies from 0 to 2 pi, and z dz, that is the length of the cylinder, it varies from 0 to L. So we can write ks cube over 3 0 to s, and phi 0 to 2 pi, and for z 0 to L, or this is equals to 1 over 3 ks cube into 2 pi into L. So this is equals to 2 by 3 pi ks cube L. Now substitute this value in the basic equation, that is this question number 1, a substitute value of E dot dA and total charge enclosed in the equation first. Then what we get? We get here E 2 pi SL, this is equals to 2 over 3 pi ks cube L. So 2 is cancelled with this, pi is cancelled with this, L is cancelled with this, and we get E equals to 1 over 3 ks2. Okay, also we have a epsilon naught, 1 over epsilon naught here, so we can write 1 over 3 epsilon naught ks2, because this is a vector quantity, so we can write s cap also. So finally we can write electric field is equals to 1 over 3 epsilon naught ks2 s cap. Okay, so this is the case related to the cylindrical symmetry, and electric field is equals to 1 over 3 epsilon naught ks2 s cap. Now we will discuss third application related to plane symmetry. So according to this application plane symmetry, we have a problem, that is, suppose we have an infinite plane carries a uniform surface charge sigma. So find its electric field. Now suppose here we have this is a surface, and because this is a plane, so we have a pillbox here, this is above the surface plane, and this is below the plane, and as we discussed, A is the area of the top surface, and similarly A is the area of the down surface, and by symmetry the direction of the electric field is upward and downward. Okay, so now so this is nothing, this is a pillbox, or we can say Gaussian pillbox. So again we apply the Gauss law. So according to Gauss law, E dot dA, this is equals to 1 over epsilon naught total charge enclosed. So here E dot dA is equals to E, and here we have a dA. So in this case the total area is equals to 2A. Why it is 2A? Because A is the area of the top surface and 1A is the area of the lower surface, and so finally we get A plus A 2A, and here these sides will not contribute in this area. And second point here is, that is total charge enclosed. This total charge enclosed is equals to, as we discussed, this is sigma, okay, sigma A. Total charge enclosed, this is equals to sigma A. Now substitute these values in equation first in the basic relation, so we can write finally E 2A, this is equals to 1 over epsilon naught sigma A. Or so A is cancelled with this, so we can write E is equals to 1 over 2 epsilon naught into sigma, and because to make it vector quantity we can write n cap also. So here n cap is a unit vector, so n cap is a unit vector pointing away from the surface. So here in this lecture we discuss the applications of Gauss law, one related to spherical symmetry, second related to cylindrical symmetry, and third plane symmetry. Thank you.